This video is about the chapter focused on linear regression with one regressor, and it comes from two chapters, one from this book, and now here we have links within the PDF, chapter 3 from O and chapter 4 from Hags. It is assumed that every student has read these chapters, as this video and this note only provide you examples of how to apply the concepts in those chapters to our data sets. As usual, the logistics, this is very standard. We have done it before. The only difference is the change in the name of the folder, but you should follow as with the previous videos and notes. We have within our packages, we have 3 new packages, so you must install those in the console. Make sure you do that before you run it, otherwise you're going to have issues. So now for the lecture, the mini summary I'm going to give you from the chapter. So the main goal of this topic is to understand how y is related to x. And just some basics, our y is the dependent variable or our outcome variable, and we illustrate that on the vertical axis. And then the x is going to be our independent or explanatory variables or covariate or regressor, and we put that on the horizontal axis. We're going to start with the simplest model where we only have one x, but then we're going to add more x's as we move to the next chapters. So as I said before, to showcase the lessons from this chapter, I'm going to go over examples with our data sets, but this video assumes and takes as given that students have read the chapters. The main assumptions of our model, which is captured by this equation, we have a y that is our dependent variable, and that dependent variable is affected by an x, and we observe y and x, but we have an error term that captures any unobservables. In one of the books, the error term is portrayed by a u, and the other one is by an epsilon. And the least square assumptions are 3. First, the error term u sub I has conditional mean 0, given that the expected value of u given x is equal to 0. And the second assumption is that x and y are independent and identically distributed. This is really referred to as IID, draws from the joint distribution. And last, large outliers are unlikely. So x and y have non-zero finite fourth moments. You can see Hags chapter 4 for more details. Econometrics with R.org, the Hags book, offers great examples to understand the model. So for example, here is telling you what the beta 1 hat, the coefficient on x, our only regressor, is going to represent. So you can read all these details. Even though the formulas presented above may not be intuitive at first glance, this following interactive application helps you understand the mechanisms of the OLS. So the idea here is that you're going to start putting dots into the figure. So you can start doing this, and you see that if I add 1 below, the slope is negative. We can see that the beta 1 hat is changing, it's negative. But if I add points this way, I'm suddenly changing the relation so that it is positive. And you can see that by the change. So you can play around with this, you can make multiple dots, and it's a great tool. The other part that tries to explain the least square assumptions that we just went over, beta hat 0 and beta 1 hat have a joint normal sampling distribution. And what this means in this interactive model, so you should read all these details, is that if we have an interactive simulation that continuously generates random samples for x, I, and yi of 200 observations, where the expected value of y given x is 100 plus 3x, and this estimates a simple linear regression model, stores the estimate of beta of the slope of beta 1, and visualize the distribution of that beta 1 hat, observed so far using this histogram. The idea here is that for a large number of beta 1 hats, the histogram gives a good approximation of the sampling distribution of the estimator. And by decreasing the number between the two sampling iterations, it becomes clear that the shape of the histogram approaches the characteristic bell shape of a normal distribution. So let me do that. If I move down here, it's going to do it faster, as you can see. And I can even do smaller. It's doing very fast. It's pretty amazing. And then you see that it's indeed approaching the normal, the bell curve. So you can play with this. The last part of this first video for this topic is about interpretation of coefficients, and students typically struggle with this. So first, we need to understand, if I give you the model that you see at the top, this is what is called a level model, because neither x or y have been transformed. And for a level model, your interpretation of the coefficient, and by the way, I'm going to clarify, b sub 1 really in econometrics is beta 1 hat. So we estimate our model, we find a beta 1 hat, and we're going to interpret that as follows. Increasing x by 1 unit, so it's super important that we know our unit, changes y by beta 1 units. So depending on the units of y. So that's what a level model is. But if we have any transformation of either the y or the x, then we change the specification. So first, let's look at the second specification where I'm denoting as b. I'm labeled them by letters. B is a level log model. Level is because the y is the level, and then log because the regressor, the x, is transformed by the natural log. So one quick clarification, within R, we're going to use the function log, but this is really the natural log, which in mathematics is just ln. So that's our second model, and then the way we would interpret this, I'm going to show you in a second, because we're going to move to another table that makes it easier. And then we could have a third specification, which is log level. So now we transform y using the natural log and keep x as a level. Lastly, we're going to see the specification D, which is log, and we're transforming both y and x. And here, what's cool is that we are looking at the elasticity. Elasticity is a concept you have learned in Intro to Micro and Intermediate Micro, but now you can see how researchers and economists may estimate that elasticity by running a regression with a log specification. Hags does a very nice job in chapter 8, which I know is not part of this notes, but I'm just taking the box from that chapter, and it tells us basic information for models B, C, and D from the first table. Our first model, A, is not there. The interpretation of the level model is given in the table before or above. But if we have specification B, or in this table is 1, we have a level log. And here, the way we interpret it, the beta 1 hat is as follows. A 1% change in x is associated with a change in y of 0.01 times beta 1 hat. If we move to the log level specification, then the interpretation is different. And it is that a change in x by 1 unit is associated with 100 times beta 1 hat % change in y. And lastly, the log specification, it says a 1% change in x is associated with a beta 1 hat % change in y. So the beta 1 is really the elasticity of y with respect to x. Anytime I give you an assignment where you have to interpret coefficients, you should go back to these two tables and make sure you understand the units of x and y. And then if there's any transformation of x or y, you need to understand the model specification so that you interpret the coefficient accordingly.